So hello friends, welcome back to my channel Canvases. So in this lecture I am going to discuss about the Newman projection. So in this lecture I am going to describe you how you can draw these types of Newman projection of any three-dimensional molecule. So this is the one thing, and what is called the conformer and what is called the conformational analysis. So all those things that these are the things that I am going to cover in this lecture. So the first thing is Newman projection. Okay, so let's see this types of bond. Okay, so suppose A and B, these are two different groups. Okay, they are the center of this A and B are basically carbon molecules, and the A group can be any group like methyl group or ethyl group. Similarly, B is another groups, and they are bonded to each other by sigma bonds. Okay, so now we knew that there can be a free rotation around this sigma bond. Okay, so that is allowed in case of sigma bonds, but this is not allowed in case of double bond. But in case of single sigma bonds, the free rotation is allowed. Okay, so during that free rotation there can be change of conformation. Okay, so while there is a free rotation around these sigma bonds, there can be change in conformation. So you may ask the question to me that what is called the conformation. Okay, so let's let's understood this concept of conformation through this simple example. Okay, so these are, you can see, these are two carbon centers, and A, B, C, these are different. It can be different atom, or it can be different groups like methyl groups or ethyl groups, or it can be hydrogen atom. Okay, so you can see that this carbon atom is bonded to three different sigma bonds. Similarly, this carbon atom is also bonded to three different sigma bonds. Okay, now you can see that these groups are basically oriented in a space in a three-dimensional way. Okay, so you can see that what is the difference between this molecule and this molecule A and molecule B. What is the difference? You can see that the main difference is the orientation of these groups. Okay, so in this case you can see that this D groups in the upward direction. Okay, but in this case this D group is in the downward direction. Okay, so this occurs due to the free rotation of this along this sigma bond. So if you just rotate this group along the sigma bonds, this D will come down, and you can see that this F group will come towards the right side, and this E group will come around the left side, and we will reach this structure. So you can see that these two structures are basically same because they have the same bond connectivity. However, the three-dimensional arrangement of these groups in the space is different. So that's why they are called the conformer. Here one point to be noted, that we are not calling them stereoisomers. Instead of that, we are calling them conformer because these two forms can be easily interchangeable. So A can be converted into B, or B can be easily converted back to A by a simple free rotation around the sigma bond, which is not possible in case of stereoisomer. So if A and B are two different stereoisomer, they cannot be easily convertible, but in case of conformers they can be easily convertible. So the rotation barrier is very negligible because the energy needed for the rotation around this sigma bond is very low. So that's why, as the rotational barrier is very low, so one conformer can be easily converted to another one. So however, they have some different three-dimensional structure, so they are called the conformers. Okay, now these are basically ball and stick model. Okay, so to draw these types of ball and stick model, it needs little bit of time. Now to save our time as well as efforts, there is one theory, or there is one way of drawing these types of three-dimensional organic molecules, and this concept of drawing is called the Newman projection formula. Okay, so you will see how to draw these types of Newman projection formula. So first of all, to draw the Newman projection of any these types of three-dimensional conformer, you have to draw first one circle. Okay, now suppose we want to draw the Newman projection of a molecule. Okay, and we are seeing in this direction. So this is the direction in which we are seeing. So you can see that this atom, this carbon atom is in our front side. Okay, and this carbon atom is in our back side. Okay, so the front side carbon atom will be drawn like this. Okay, so this is the D group, this is F, and this is E. So this is our front side carbon. Okay, now if you just go through and through of this circle, you will reach the back side of this molecule. Okay, so the back side of this molecule, you can see in the left side there will be B group, and in the right side there will be A group. Okay, so we will draw like this, and in the lower direction there will be C group. So you can see this is the Newman projection of this A molecule. Similarly, you can also draw the Newman projection of B molecule. First of all, you have to draw the circle. So you are looking this molecule from this position. So this is your front carbon. Okay, so according to this position, in your left side E group is present, and in your right side F group is present, and D group is situated in the downward side. Okay, so the formula will be like this. Now this is your rarer side, so rarer side carbon. So the B group is situated in the left side, A group in the right side, and C is in the below side. So this is the Newman projection of the molecule B. So in this way you can draw the Newman projection of any three-dimensional conformer. So you can practice it at your own. So it will take hardly any time to draw these types of Newman projection, and if you practice it well, I am very sure that within few hours or within few minutes you can become an expert to draw these types of Newman projection. Okay, so let's go to the next slide. So these types of Newman projection has basically two types of conformation. So one is called the staggered conformation and another is called the eclipsed conformation. So in this slide I am going to discuss what is called the staggered conformation and what is exactly this eclipsed conformation is. So this is the Newman projection of a staggered conformer of ethane molecule C2H6. Okay, so this is one carbon molecule and another carbon molecule is situated at the back side of this sphere or circle, whatever you say, and these are the 6 hydrogen atoms. They are oriented like this in the staggered conformation. So you can see that in the staggered conformation the hydrogen atoms you can see are separated as far as possible. So there is maximum distance that is maintained in between this hydrogen atom in case of these types of staggered conformation. If you draw this structure, okay, in the like ball and stick model, you can see the ball and stick model, you can see that this is one hydrogen atom and this is one hydrogen. This is the top hydrogen atom. You can see like this, and this is the bottom hydrogen atom, and you can see there is the angle that is equal to 180 degree. You can see this is the 180 degree angle that is maintained between these two hydrogen atom, and this angle is called the dihedral angle or phi, that is equal to 180 degree. So as this dihedral angle increases, it suggests that the distance between these two hydrogen atoms are very much. So you can see that this hydrogen and this hydrogen atom are very much far apart from each other. Similarly, this hydrogen, these two hydrogen atoms are very much far from each other. Similarly, this hydrogen and this hydrogen atom. So these dihedral angles are 180 degrees. So as you can see that these hydrogen atoms are separated as much as possible in case of staggered conformation. So okay, so here you can see that I have already told you that the angle between this hydrogen atom and this hydrogen atom is 180 degree. This is called the dihedral angle. Similarly, the angle between this hydrogen atom and this hydrogen atom is 60 degree. Okay, so this is the staggered conformation of ethane molecule C2H6. Okay, understood. Now coming back to the eclipsed conformation. So this is the Newman projection for eclipsed conformation. So eclipsed mean that two things are overlapped with each other. So you know that in case of solar eclipse, what happened, that the sun and the moons are almost actually shadowing each other, or we can say that the moon is shadowed by the sun. Okay, now coming back to the eclipsed conformation. So what happened in case of eclipsed conformation is that you know that in case of any eclipse structure, the two things or the two substances are almost merged with each other. So that is called the eclipsed. Okay, so that is happened in case of solar eclipse. So you can see that the two things are merged with each other, which is exactly happened in this case. You can see that this CH bond, and that is the front side CH bond and the back side CH bond, they are aligned in the same direction. You can see similarly this CH bond, this CH bond, and this CH bond and this CH bond, all the CH bonds of front carbon and back carbon, they are almost or exactly aligned with each other. So that's why the dihedral angle between these two hydrogen atom, that is equal to 0 degree. Okay, similarly in this case also the dihedral angle is equal to 0 degree. So this is the ball and stick model for the eclipsed conformer. So here you can also see that the dihedral angle is equal to 0 degree. So this is eclipsed conformer and this is the staggered conformer. Okay, now we will learn about the conformational analysis of ethane molecule. Okay, so what is called this conformational analysis? Basically in conformational analysis we try to draw the all the possible conformers of any molecule, and we will try to determine its energy. So we will draw some kinds of this types of plot. In the x-axis there is a rotation, that is as we are going from left to right direction, there is a rotation around the CC sigma bond, and in the y-axis we will draw the potential energy of that conformer. Okay, so first of all let's see the staggered conformer of ethane molecule. Now you can see that the staggered conformer is called to be the most stable conformation for ethane molecule. So why it is that? Because in case of ethane molecule there is maximum possible separation between these CH bonds. On the other hand, in case of eclipsed conformation, these CH bonds you can see are very close to each other. So what happened in that case, that the electron density that is associated with this CH sigma bonds, they are also very close to each other. So there will be the electronic repulsion of this electron clouds that is associated with this CH bond and that CH bond. So due to that electronic repulsion, the potential energy of the eclipsed conformation increased very much. So the main difference occurred due to this electronic repulsion factor between the staggered conformer of ethane and eclipsed conformer of ethane molecule. Okay, so let's see how it's look like in energy or potential energy diagram. Okay, so you can see that this staggered conformer, it is the, as in case of staggered conformer, the electronic repulsion factor is not there, so its energy is very minimum. You can see this is the minimum energy. However, if we this rotate around the CC sigma bonds, then we will reach this eclipsed conformer, and in case of this eclipsed conformer, due to that electronic repulsion factor, there will be a huge jump of potential energy. Okay, again if we rotate this CC sigma bonds, then this hydrogen atom will again come to this position, this hydrogen will be in this position and this hydrogen will be in this position. So we will again reach the staggered conformer. I have drawn it, sorry, I am drawn it actually wrongly. It will be again the staggered conformer like this. Okay, so you can see that the energy barrier for while rotation around the sigma bond, that is like this is the energy barrier, and the energy barrier is 12 kilojoule per mole. Now this energy barrier is not so high that rotation can be retarded. Okay, so the rotation is very much possible at room temperature because this energy barrier is not so high. Okay, but on the other hand, as this staggered conformation is the most stable conformer of ethane molecule, so at any given moment, in the case of ethane molecule, the number of molecules having the staggered conformation will be always greater than the number of molecules having eclipsed conformation. Okay, so at any given time we may have 75% staggered conformation and 25% eclipsed conformation, but we cannot actually distinguish or separate out these two conformation, as they are readily convertible into each other. However, if we can separate out in any way theoretically at any given moment, we will see that it is always the staggered conformation will be present in a larger number compared to the eclipsed conformation. Okay, now we will move to a bit complicated molecule for conformational analysis. So we will go to the conformational analysis of butane molecule. So this is the structure of butane molecule: CH3, CH2, CH2, CH3. So 4 carbon atoms are there. So we will be mainly interested for the conformational analysis due to the conformer that is formed due to the rotation of C2C3 sigma bond, rotation around this bond. So due to this rotation, whatever the conformer that is being formed, we will see what are their energy levels. Okay, so you can see that this so the main factor we will see in this case, which basically decides the energy of this conformer that is produced due to the rotation around the C2C3 bonds, is the torsional strain. So in the next slide, I will discuss about what is called this torsional strain and how it affects the energy barrier or energies of different conformer. Okay, so you can see that these are the 6 conformer that is formed in case of butane or the rotation around the C2C3 sigma bonds. Okay, again you can see that I am just drawing the molecule for your convenience. The butane molecule like CH3, CH2, CH2, CH3. Okay, so this is C1 carbon atom, this is C2 carbon atom, this is C3 carbon atom, and this is C4 carbon atom. So we are interested for the conformer that is formed due to the rotation around this C2C3 sigma bonds. Okay, now you can see that this carbon atom is attached with one methyl group and two hydrogen atom. Similarly, this C3 carbon atom is also attached with one methyl group and two hydrogen atoms. So these are the six conformer that is formed due to the rotation around this sigma bonds. Okay, now as you can see that the first conformer that is I have drawn here is called the anti-conformer. So you can see this is basically staggered conformation, and you can see that these two methyl groups are basically very far apart from each other, and the dihedral angle between these two methyl groups is equal to 180 degree. Okay, so this is called the anti-conformer. Now if you just rotate this sigma bonds around 60-degree rotation, if you give around the sigma bonds in the clockwise direction, then this hydrogen atom will come at this position, this hydrogen atom will come at this position, and this methyl group will come at this position. So we will get this eclipsed conformer. Okay, so you can see that this is called the eclipsed conformer. Again, if you give the 60-degree rotation, this hydrogen atom will be in this position, this hydrogen will be in this position, and this methyl group will be in this position, and we will get this conformation, so or this conformer. This is also a staggered conformer. However, you can see that there is some steric repulsion that will be occur between these two methyl group, because in this case, that is the main difference between this staggered conformer and this staggered conformer is this two methyl group in this anti-conformer is much more far apart compared to this two methyl group, because here the torsional angle or dihedral angle between these two methyl group is 60 degree. On the other hand, in this case, the dihedral angle between these two methyl group is 180 degree. So there will be much more greater steric repulsion between these two conformer. So although it is a staggered conformer, but still its potential energy will be higher due to the close proximity of these two methyl groups, and this conformer is also called Gauge conformer. Again, we give 60-degree rotation around this clockwise direction, and we reach this eclipsed conformer. So in this case, you can see that these two methyl groups are almost merged with each other. So the dihedral angle between these two methyl group is 0 degree, which causes much more severe torsional strain compared to this Gauge conformer, because they are the closest one. These two methyl groups are very close to each other. So that's why in this eclipsed conformer the energy will be very high. Again, if you give 60-degree rotation, you can see that this methyl group come at this position. Okay, so you will get this Gauge conformer because these two methyl groups are very close to each other, dihedral angle 60 degree, and this Gauge conformer, that is conformer number 5 and conformer number 3, they will have same energy. Okay, there is no difference between these two conformer energetically. Again, if you rotate 60 degree, we will reach this eclipsed conformer or conformer number 6. This is eclipsed one, and this will have the similar energy like this second eclipsed conformer. So you can see this is the conformational analysis of this butane molecule due to the rotation around the C2C3 sigma bonds. In the x-axis, it is basically the rotation around the C2C3 sigma bond, and the y-axis potential energy. So you can see that this anti-conformer will have the lowest energy because there is no torsional strain at all present in this anti-conformer. Now in the eclipsed form, you can see that there is a huge torsional strain between this CH and this methyl group and this hydrogen atom. Okay, so there is a steric hindrance between this CH and CME. Okay, so there will be torsional strain, and due to that torsional strain the energy will be increased. in the eclipsed form. Again, if you go to again the staggered conformation or the gauge conformation, the energy will be little bit reduced, but still the energy will be not as low as anti-conformer. As I have told you that in this case there will be still some steric hindrance due to the close proximity of this two methyl group, because the dihedral angle in this case is 60°, which is closer compared to anti-conformer. So that's why it will still have some extra potential energy compared to this anti-conformer. Again, 60° rotation give this eclipsed conformer, that is eclipsed conformer number 4, and in this case there will be a maximum repulsion or maximum steric hindrance, because there will be steric repulsion between two methyl group. You can see that in this the main difference between eclipsed 2 and eclipsed 4 conformer is that there is a steric repulsion between methyl and hydrogen group, and in this case there is a steric interaction or repulsion between two methyl groups. So here both methyl groups are bulkier, so that's why the steric repulsion is much more higher compared to this eclipsed one. So that's why this conformer will have the maximum energy. Again, 60° rotation will give this gauge conformer, and this gauge conformer will have same energy like third gauge conformer. You can see these two are having the same energy. Again, 60° rotation will give you this eclipsed conformer, which is having nothing but this one. This is having the same energy like the number 2 conformer, that is like this. Okay, and again if you give 60° rotation, again we will reach this anti-conformer, which is again having the lowest energy. So this is the full conformational analysis of butane molecule around due to the rotation around this sigma bond, C2C3 sigma bonds. Okay, so I hope that you have understood this lecture, and if you have any questions or doubt in this lecture, you can ask me through the comment section. And if you do like this video, please subscribe to my channel Chembiosis. Thank you very much.